In this segment, we're going to see how to analyze our delta-delta-CT study using ExpressionSuite, including how to interpret the various graphs and charts that the software presents as part of the output, and we'll see how to export the final data. We'll start where we left off in video 3, the Run QC segment of the workflow. To see our data, we'll click on Results, where we find buttons for 5 different plots. The first one, Correlation Plots, presents our data in a fairly traditional way. It contains a list of technical replicates grouped as sample gene pairs, along with CT mean, adjusted CT mean, which we'll explain a little later in the video, delta CT mean, and standard deviation. We can group the data either by sample name or by the gene, just by clicking the corresponding column header. We can also group the data by biological replicates, assuming we've labeled these. Doing so also changes the graphical view of our data below. I'll choose technical replicates for now, since that gives us more data to look at for demonstration purposes with respect to our 2 plots at the bottom. Speaking of which, to the left is a correlation scatter plot. It shows the correlation of either delta CT or CT, depending on which we select from this pull-down menu, across all targets for any pair of samples or biological groups. The screen to the right is a signal correlation plot and presents the correlation coefficient, or R, for each pair of samples inside the appropriate box. I'll just click this plus sign so we can read our rather long sample names. Okay, so the way this works is, the greener the box, the closer the value of R is to 1, and therefore the more correlation between the 2 samples or biological groups in terms of either CT or delta CT. Here's an example. Say we select a box with a correlation of 1. It has that value because, well, it's the same sample. We'd certainly expect every gene over here on the left to have exactly the same delta CT since we're comparing a sample to itself. Well, let's use a different example. Here's a red box, meaning these 2 samples have a much lower correlation. When we click that box, we notice in our correlation scatter plot that some of our genes have quite different delta CT values between these 2 samples, just what we'd expect. One side note, with delta CT selected, our normalizer, beta-actin, is always located at the origin, regardless of which block I choose on the right. And that's because in every sample-to-sample comparison, actin CT is being subtracted from the target to generate those delta CT values. We'll next go to gene expression. We find the standard delta-delta CT calculations at top, including several from the previous graph. In addition, we have a column for RQ, or relative quantity. This one is our all-important sample-to-sample fold change, with each biological sample being expressed as a fold change in expression relative to our reference biological group. We only have 2 groups in our study and only 4 target genes. Thus, 4 of our sample gene pairs have values of 1, those belonging to our reference biological group, while the other 4 have some fold change, either higher or lower, relative to that reference biological group. Clearly, the software has ducked as the reference group such that all tubule samples are being compared to it. Did we make that choice? Well, no. The software automatically chose a reference sampler group for us. However, we're not obliged to stick with its choice. We can go to Analysis Settings, Relative Quantification Settings, and, using this pull-down menu, choose a different group. Hitting OK and Analyze will now cause the tubule biogroup to have a value of 1 for each gene, and all duck samples to have some relative fold difference. Well, what about these RQ-min and RQ-max columns? Well, what these represent are likely high and low values for that sample or biological group based on a confidence range that defaults to 95%. Let's go back to Analysis Settings for just a second. Notice that we can either change that RQ-min, RQ-max confidence value, or we could even choose to use the more traditional standard deviations. Our choice will of course determine how the final error bars are drawn here in the RQ plot. And speaking of which, looking at our lower graph of relative quantities, we have some rather large error bars that are really stretching the graph out. Now, that's not due to an error on anybody's part, but rather to some large biological variability among our rather small sample set. A few points about this graph. First, relative quantity is always on the y-axis. However, the x can represent either our individual samples or biological groups, or our various targets. Now, I prefer the second way since I generally want to see my biological groups compared to one another within individual genes. Using a view, we can actually get rid of the error bars if they're being a nuisance. We can then go under Plot Properties way over here on the right and rescale the y-axis manually. Back under View, we can add different labels to the graph. Other options. We can scale and log instead of linear on the y-axis, and even go from a vertical to a horizontal view. Finally, we can right-click and either print our graph or save it as a high-quality JPEG, two options which, importantly, we have with all graphs and charts in ExpressionSuite. I want to look more closely under Analysis Settings and Relative Quantification Settings, and all of the options we have there. Now, we already discussed reference samples or groups, as well as RQ-min max values. One thing we didn't talk about is the checkbox next to Benhamini-Hochberg false discovery rate to adjust p-values. Let's spend just a minute on this concept. Let's say the goal of our experiment is a fairly common one, to look at a large group of genes in our untreated and treated sample groups, and to identify a subset of genes that show a significant fold change difference. The final list, which we base on p-values, may consist of 20 genes. But probably not all of those genes will truly be significant. And that's because there's a certain error rate that leads to false discoveries, or we might say false positives. Benhamini-Hochberg is an algorithm that adjusts p-values in an effort to compensate for this error, and thus to weed out those genes that aren't really showing significant expression variation among our biological groups. For more information on how the algorithm works, pause the video and have a look at this description, or simply have a look at the original paper online. It's available for free. By the way, if we select to not use the Benhamini-Hochberg algorithm, you'll notice that the far right column goes from adjusted p-value to plain old p-value. Two other features under Analysis Settings to mention. We can set a maximum allowable CT value for our study and make the choice of whether or not this value should be included in calculations or not. We need to be cautious with this one. If we decide that we want a CT of 35 to be our highest value, but we also leave this box checked, then all samples above 35, even wells that failed entirely, will be imputed to 35 and included in the final calculations. My preference, generally speaking, is to leave this unchecked, which will cause samples of the maximum CT and higher to be rejected outright. By the way, one of the columns under gene expression that I said I'd talk about later, namely adjusted CT mean, this data reflects whenever CTs do get imputed to the maximum value. Finally, there's a box for entering individual assay efficiencies. As you know already, ExpressionSuite is designed specifically to do delta-delta CT analyses, but you may also be aware that when assays amplify with less than 100% efficiency in the geometric phase of PCR, this can have a detrimental effect on final data when using the delta-delta CT calculations, which otherwise assumes 100% efficiency. To correct for less than optimal assays, some users may want to enter the empirically determined efficiencies for their various assays, such that the final math performed by ExpressionSuite will take these into account. The good thing is that if you're using gene expression assays from Life Technologies, this correction is generally not necessary, as the vast majority of our assays have been shown to work at or near 100% efficiency. Let's go back to the workflow menu and choose RQ Settings Comparison. This is a really nice feature that's also available in some of the newer real-time instrument software. It allows us to try out two different sets of analysis parameters and to compare the results from both side by side. The lower left pane represents the data as currently being analyzed. Over to the right, notice how several analysis parameters can be adjusted without going under analysis settings. We can make one or more changes, click Test New Settings, and see how things look. If we decide to go with the new parameters, all we have to do is click Apply New Settings to Study. Heat map is the next option under the workflow menu. For anyone who's run microarrays before, heat map should look pretty familiar. These are graphs that use color coding to map out similarities in expression across our samples and genes, and that cluster these hierarchically, often allowing us to recognize important relationships among particular samples or genes. We don't have time to cover heat maps extensively, so I'll just mention a few capabilities here. We can use either Euclidean distance or Pearson's correlation to create clusters. We can change the clustering method, change the map type, which I'll give a bit more information on in a moment, or alter the color scheme. Pause the video here for a minute and read how the assay-centric, sample-centric, and global views give you different perspectives on the same data. Or you can have a look at some references that discuss hierarchical clustering in detail. Finally, let's see the Volcano plot. This is a useful graph for visually separating out biological groups with fold changes that exceed a set cutoff and do so with p-values considered significant. We can choose the group to be considered, and we can set our fold change boundary by either entering a value here or by dragging the black lines. Essentially, groups have to have a fold change relative to the reference group that's outside these boundaries in order to be considered significant. Black dots represent samples that don't meet or exceed the current p-value and fold change cutoff, while green and red dots do. Greens represent a significant decrease in expression relative to the reference group, and red represent an increase. Well, the last thing we want to do is export our data. This part's easy. We start by clicking the Export button. By default, only the tabulated results will be exported, though clearly we have other options. Also, we may export our numbers as a tab-delimited text file, or choose one of these Excel formats. If we want to get rid of any columns prior to export, we simply uncheck those boxes. And once we're ready, we browse to the location on our hard drive where we want to save the file, and then click Start Export. And that's it for analysis and exporting. I hope you now have a much better understanding of the basic analysis features of ExpressionSuite. In the next video, we'll see how to set up and use the optional auditing and security features within the software, a really important feature for regulated and security-focused labs.